The present study introduces a three-dimensional multi-level model to assess the structural response of real-scale structures subjected to flash flood events. The proposed framework operates on two distinct but coupled scales. At the macro scale, a computational fluid dynamics model simulates the impact of the water flow on a rigid solid domain, allowing us to compute the hydrodynamic pressure at each time step. Simultaneously, at the meso-scale, the structural response is evaluated using a nonlinear coupled damage-plasticity model, where the pressure data from the macro-scale analysis are transferred as dynamic loads acting on the structures. The multi-level model is first employed to simulate the impact of a fluid flow on a rigid solid structure within the macro-scale domain. The maximum pressure on the wall peaks rapidly as the fluid strikes the surface, then progressively stabilizes, indicating the onset of a quasi-steady flow condition. The pressure maps extracted from the macroscale analysis are used as input for the structural simulation. Here, the structural response is analyzed. While the macro model assumes a rigid body, the meso-scale model accounts for nonlinear structural behavior. The comparison with the static model highlights that the predicted dynamic load aligns with the static assumption only after flow stabilization. However, standard codes tend to be conservative. Damage maps at different time steps show that the highest structural damage occurs in the stabilized flow phase. The damage is distributed in bands from the center toward the edge, unlike the static case, which produces a less realistic localized damage pattern. The results confirm the good numerical capability of the proposed approach even under extreme loading conditions.